Hi guys, and welcome to lesson 2.2, Intro to Systems of Equations. After this lesson, you should be able to recognize what a system of equations is, as well as you should be able to explain what a solution to a system is. And finally, you should know the three cases of two linear equations. So there are systems of two linear equations, and there are three cases of those. And lastly, you need to know how to solve a system of equations graphically or visually if you want. Okay, so let's get started. And before we can solve a system of equations graphically, we need to know what a graph is. So basically, a graph is a relationship, okay, between an equation. So say, for example, y equals negative 2x plus 4. It's a relationship between the equation and the x and y values that satisfy that equation. So it's a visual representation of that. So if we look at all the points on this line, okay, that I've labeled here, we should be able to see that all of these xy coordinates satisfy that equation. So if I sub in 8 for y, and if I sub in negative 2 for x, I should get that left-hand side equals right-hand side, and it does. Now, what we normally do in class is we generally use integers, but that doesn't mean that these other points don't also solve this equation. In fact, they do. That's why when we draw a line, we don't just draw single dots, right? We have to fill in all the spaces in between. Now, I know you are not familiar with this equation yet, x squared plus y squared equals 25. We're going to learn that in a different unit. But what we'll notice is that it's the same idea. All of these values of x, y actually satisfy this equation. 3 squared plus 4 squared equals 25. It sure does, because that's 9 plus 16 equals 25. And if I go around, again, these are integer values, but we also have some really ugly looking values that we can't really guess at, right? We might need to calculate something like that. Okay, so generally what I want you to know after looking at this page is that a graph of an equation is a visual representation of all the xy values that satisfy that equation. So there we go. Okay. What is a system of equations? So a system of equations is two or more equations associated together using one of these brackets. So if you'll notice, there's one down here. And what that means is these two, I know you don't know these equations yet, but they are associated together in a system by those brackets. Now, what is a solution to a system? Well, if I have two or more equations, when I graph, I'll have two or more graphs. And a solution to the system is any points that exist on both graphs at the same time. And what that means is, so if I zoom in on something like this, I know that actually these 2 points here in pink, okay, this one is 2, 0, and this one is 0, 2. Both of these points are actually on both the line and the circle. So there's solutions, x, y, that exist on both equations. Now, what does that look like visually? Well, it looks like points of intersection, right? So we can say visually, okay, if I look at these systems, I can see just by looking how many solutions each of these systems has. So this one here we can see has 4 solutions. This one has 2 solutions. This one has 0 solutions. How do I know what's happening outside of this field of view? Well, we always assume that these things keep doing what they're doing, okay? And that they're not going to do anything funky outside of the field of view. So we know that these two are not going to intersect because they're not intersecting in the field of view, okay? And this guy has 3 solutions. So even though you don't know these equations, visually speaking, you can see that the solutions are points of intersection because they are points that satisfy the equations simultaneously, okay? So if I were to consider the following system and the graphs, okay, so I've graphed both equation 1 and equation 2. So equation 1 is a circle of radius 5 centered at the origin, and equation 2 is a line. We can pretty clearly see that there are 2 solutions, and the first one is 5, 0, and the second one is -3, -4, and that's part A. Okay, the solutions are okay. Now it says check your answer by subbing the values into the equations to ensure that left-hand side equals right-hand side. All right. So to check 5, 0, okay, 5 squared plus 0 squared equals 25, question mark? It does. Y equals 5, oops, I should be subbing in 0. So 0 equals 1/2 5 minus 5 over 2. Well, yep, that is also 0. That is also true. Let's check -3, -4. All right, so that's what it means to be a solution to a system. All right, now, what does a system of 2 linear equations look like? So what I'm going to do is actually explain this using examples. So we're going to get really fast at graphing lines. If you remember, we're going to graph the first one. We start with the y-intercept, and then we use the slope, which is 2, okay, to draw the rest of the line. I'm going to use a ruler to make sure this is straight. Okay, and then number 2, I'm going to start at 2. I go down 1 across 2. Sorry, up 1 across 2. Okay. Okay, and I can see this has a point of intersection right here. The point of intersection is 2, 3. All right, I'm going to graph the next one. All right, so let's have a look at this. There are 3 different scenarios you can have when you are graphing a system of 2 linear equations. So not circles, not parabolas, not the other ones, but when you have 2 lines being graphed. So as we can see through these examples, there are cases where we have one solution, okay, where we have infinitely many solutions. And why is that? That's because these 2 lines are overlapping. So any xy value that satisfies the blue line must also satisfy the red line. And now in the last scenario, there are actually no or zero solutions because these two lines don't have any xy values in common. Okay, so we can see visually, it's really nice to see this way how many solutions there are, but let's look at how this is associated with the system. So if I look at the slopes of the red and the blue lines in the first example, we'll see that the slopes are different. Okay, and the whole point here is as long as two lines have slopes that are different, they will always intersect. Always intersect somewhere, okay? And so this doesn't actually really matter. It doesn't matter what the y-intercepts are in this case, but as soon as I know that the line slopes are different, I can say that this system is intersecting. That's what we're going to call this type of system, intersecting. Now in the second case, where my red and my blue line overlap each other, we're literally going to call this overlapping. So a very suiting word. Okay, really what we should be saying is parallel and coincident is probably what you'd see in textbooks. Coincident. Okay, like as in a coincidence, they both happen at the same time. And what we'll notice that both the slope and the y-intercept have to be exactly the same. They're literally, again, the same line. Okay, last case, we're going to call this case parallel. Okay, and in a textbook, you might see this as parallel and distinct. And what I found in the past is guys tend to get these two kind of confused, which is why I'm using the word overlapping to describe scenario 2 and parallel, even though, yes, they're both parallel, but we can call this parallel as in never going to touch. So we know that the slopes are the same, and in this case, the y-intercepts have to be different because if they're the same, then you're in the case of overlapping. So that's a nice little summary there of the three possibilities when you have a system of two linear equations. So now what we're going to spend the rest of our time doing is just solving some points of intersection graphically. So what I want us to do is get really quick at graphing lines. Okay, so to graph a line, I'm always going to want to put it in y equals mx plus b form. And then I start with the y-intercept and I use the slope. I use the slope to help me locate other points. All right, so we're going to need a sentence answer here. Okay, the solution to the system is -6,5. Let's give the other ones a try. Okay, so I just wanted to go over labeling. We should really be labeling all these lines on the graph. And what happens when I have three linear equations associated in one system? Well, same deal. As long as all three lines have one point of intersection, okay, an xy value that solves all of these simultaneously, solves meaning left-hand side equals right-hand side, all three at the same time, or I don't even have to say that, solves all three of them, we know that that is a solution to the system. All right, let's try these next two. Okay, so what do we say in this case? Well, I can't just leave it like this and not give a sentence answer. Okay, so what I have to do is I have to, with my words, say there are no solutions to this system. Because if I just leave it blank, it's going to look like I don't really know what kind of system this is. It looks like I left it blank because I didn't know. So I need to write a sentence here to inform other people that I know actually there are no solutions to this system. Okay, so when I have infinitely many solutions, there are infinitely many solutions to this system, right? What I need to also do is give 3 examples, okay? So in this case, for example, now I can't just pick random x and y values. They just have to be x, y values that are on these lines. So for example, I can pick this one here. For example, I have -2, -6. Another point is this one, 4, 3. And I can pick this one as well, 6, 6. Okay, so here are my solutions. All right. Okay, so in summary, okay, in a system of 2 linear equations, there are 3 possible outcomes: intersecting, having 1 solution; parallel, overlapping, infinitely many; and parallel and distinct, or we said we can just call this parallel, having no solutions. So now we're moving into the zone where we want to try to do this without having a graph. How can I do this using just equations? So let's remind ourselves there are 2 equations of a line, 2 forms that we generally use: y equals mx plus b and ax plus by plus c equals 0, or sometimes we'll see it as ax plus by equals -c. The c can be on either side. Both of those are basically standard form. So moving ahead, I want to go over 2 facts. Fact 1 that we already said is 2 lines that have different slopes will always intersect. Okay, so as soon as I can see 2 lines from their equations have different slopes, I know right away they're intersecting. Now, when the slopes are the same, that's when we have to distinguish whether they're overlapping or parallel and will never meet. So fact 2 is something that we have to keep in mind. Multiplying all the terms in the equation of a line by the same number, so like scale up or scale down ratio, it doesn't change the line. So if I want to give 2 examples of 2 lines that overlap with this one thing I can do is I can multiply all of these by 4, okay, and I know that's the same line, okay, or I can multiply all of them by 2, okay, and I know all 3 of these lines, when I graph them, they're going to be the same. Okay, this is just, it's algebra. If I do something to the left-hand side and the right-hand side, it doesn't change the actual line. So now in this standard form where C is on this side, if I want, I can divide all of these by 2, and that's going to be the same line. Or I can multiply them all by, I don't know, -3. If I multiply this by -3, I'm going to get -6y plus 24x equals 30. So all 3 of these lines, if I graph them, they'll be the same. Okay, so in summary, when I look at the equation of a line, and I'm going to use, this is like in standard form, okay, but it works too with y equals mx plus b. Basically, I know I have infinitely many solutions if the coefficients are ratios of each other. All 3 of the coefficients of the first line are a ratio of all 3 of the coefficients in the second line. So here are two examples. I can clearly see that the second line is times -2 of the first line, all three of the numbers. And when I write it in y equals mx plus b form, it's really obvious that they're the same line. Okay, so both of, and when I have something in y equals mx plus b form, I can see it really clearly. I have no solutions, okay, so these coefficients here, a and m, and b and n, those tell us about the slope of the line. So if those ratios are the same, the slopes are going to be the same. So as long as these two ratios are the same, I know the slopes are the same. Now this last one here, the C and the P, if that ratio is the same as the other two, then we're in the infinitely many solutions case, but meaning that they're overlapping. But if they're different, what that ends up looking like is the same slope but a different y-intercept. So I can see that in this case, the 3 and the -6 are times 2. The -4 and the 8 are times 2, but I can clearly see that this doesn't share that ratio. So I know that these are parallel and distinct, okay? And then lastly, maybe the easiest case is if my slopes, okay, if the A, B, M, and N don't share a ratio, then I know that these have different slopes. So I can see pretty clearly here that the ratio here is -2, but the ratio here is not. Okay, that's -2.5, I think. So right away, I know that the slopes are different and they're intersecting. And again, it's easy to see y equals mx plus b, they're different slopes. So let's put this information to the test. Without graphing, I want to classify each system as overlapping, parallel, or intersecting. So what I want to do, first I'm going to look at the first coefficients. Okay, and I can see that I have a ratio of -3 over -5. And then I'm going to look at the second coefficients, and I see that I have a ratio of 3 over 1, and these are not the same. If they're not the same, that means they have different slopes. Okay, and in that case, I know that this is intersecting. I'm going to do the same thing here. All right, so I can see, oops. Okay, so for the first one, I see a -3 over -1, and I see a 3 over 1 ratio. Yes, these are the same, they're both 3. So what I have to do is make sure that that jives with these numbers here, and I can see that actually it does not. 4 over 3 is not in the same ratio. Okay, so what this means is they have a same slope but different y-intercept. Okay, so these are parallel and distinct. Okay, and last one. Okay, if I look at these, let's just highlight them all. Actually, I don't have to do that anymore, I think. So we've got 2 over -5, which does equal 8 over -20. We can reduce that actually. If we divide both by 4, yes, this is 2 over -5. And then I have 6 over -15, which, yeah, is also 2 over -5 if I divide by 3. So all three of them have the same ratio, meaning that they both have the same slope and y-intercept. So these are actually overlapping lines. And yeah, if I do look a little bit closely at this, if I multiply the first line by -2.5, all the terms, I would get the second line. So last example here, guys. definitely a question I would ask on a test. For what values of A and B does the following system have infinitely many solutions, no solutions, and exactly one solution? So I know in infinitely many solutions, if I want overlapping lines, I need the same slope and the same y-intercept. Okay, so in that case, the ratios all have to be the same. So 2 over 4 has to equal 3 over a plus 2, which has to equal 6 over 2b. So how do ratios work? Well, I can just look at these two first, and I can cross multiply. So when I cross multiply here, I can see that if A is 4, that's going to get us somewhere. And then I can look at comparing this to this and cross multiplying. So if I have 2 over 4 equals 6 over 2b, b equals 6. Okay, why don't we actually give that a try? So if I take my system 2x plus 3y equals 6, 4x plus, and a plus 2 is going to be 6y equals 12. I know this works. The second one is times 2 of the first one. Okay, so I've found the right variables, but it's saying give 3 examples of specific solutions. So I just have to find any 3 points on this line. So if I say x is 0, if that's 0, then I have 3y equals 6. So 0, 2 is going to work. Also, now why don't I make y 0? So 3, 0 is going to work. If I sub x equals 1 into this equation, okay, another value is 1 and 4/3. So all 3 of these points are on this overlapping line. Okay, so what do I have to do to have no solutions? Well, what that means is I know that 2 over 4, which is my coefficient of x, and 3 over 6 both have a ratio of 1 over 2, but I need to make sure that my last variable doesn't have that ratio. So as long as b is not equal to 6, I won't get the 6 over 12 ratio. So b can be anything but 6. So I can say a equals 4 and b equals anything but 6. For example, I don't know, b equals 5. So if a is 4 and b is 5, this isn't going to work. And you can give it a try if you want by subbing this value of a and b in and trying to solve the system. How about exactly one solution? Well, basically what that means is I need a different slope. So we said that the slopes were the coefficients of x and y if those were proportional to each other. So I have 2x plus 3y equals 6, and I have 4x plus a plus 2y equals 2b. Now remember, the y-intercept is irrelevant when I'm intersecting, so b can actually be anything at all. What I need to make sure about is that this a plus 2, okay, doesn't match up in the ratio of the coefficients of 1 to 2. So I have 2 over 4 equals 3 over, currently I have 3 over 6 when a is 4. So as long as a does not equal 4, okay, this works. This system has a solution, one solution. Okay, so we can say, for example, a equals 5 and b equals 5. But b can really be anything. Oops. Okay, guys, I'd like you to get started on the homework. I hope this video was helpful.